In this final video, we're going to look at an extension to the Debye-Huckel theory that works a little bit better to slightly higher concentrations, and then look at an example of how we can use this to calculate an activity coefficient, just a quick example. So we can take, there's an extension, we're not going to go through how this was derived, but you can take Debye-Huckel theory and extend it, and there are various ways of doing this, but we have sort of our same equation here. So negative 1.173 times the absolute value of z plus times z minus times IC in moles per liter raised to the 1/2. And the way this is extended is it adds this extra term in the denominator, 1 plus the ionic strength again, raised to the 1/2 power. And this gives slightly better results than just straight Debye-Huckel theory. So this is often the version that's used for practical purposes. For example, in the analytical chemistry textbook that we use, this is the version of the equation that's presented as the Debye-Huckel theory that you can use to calculate activity coefficients. So how do we use this? How would we find a value? So let's say we want to find gamma plus minus for sodium sulfate if it has a concentration of 0.02 molar. Okay, so we know that we have 2 sodium ions and 1 sulfate ion for every formula unit that we have, and we know that the charge for Z plus is 1 and Z minus is -2. So the first thing we need to do to be able to use this is find the ionic strength. So IC is equal to 1/2 times the charge of the positive ion squared times 2 times the concentration plus the charge of the other ion, and it's not just the positive and negative, it's just however many total ions you have in solution, times the concentration, because this is the concentration of the positive ions. Because we know we have 2 sodiums, we have to multiply by 2, whereas we don't need to do that for sulfate because there's only 1 that's produced. Okay, and if we plug that in, we'll get 1/2 times 2C plus 4C, which gives us 3 times the concentration, or in this specific case, that's 0.06 molar. Okay, and then we can go ahead and plug that into, we can go and plug that into our activity coefficient equation. So log gamma plus minus is equal to negative 1.173 times absolute value of 1 times -2 times 0.06 raised to the 1/2 power. And then if we use the extended version, we get 1 plus 0.06 raised to the 1/2 power. So you can do this with or without the extended version. If we do it without the extended version, that's the version I have in my notes here. So if we ignore the bottom here, this gives us negative 0.575. And then if we do calculate with the extended version, I'll just need to plug this into my calculator real quick. Let me go ahead and show the calculator. Oh, but don't get rid of that. Never mind. All right. We're just going to have that in the background. All right, negative 1.173 times, of course, now I can't see what I'm calculating, though. All right, I'm not going to show the calculator. All right, negative 1.173 times 2 times 0.06 raised to the 1/2. All right. And then all of that, sorry, just having computation issues. 1 plus 0.06 raised to the 1/2 gives a slightly different value of negative 0.462. Okay, so we can see we get a little bit difference between the just Debye-Huckel and the extended Debye-Huckel. And so if we want to find gamma plus minus, we would just take the exponential of these. So for example, this value gives us gamma plus minus is equal to 0.563. And this value here, if I just plug it into my calculator real quick, we get 0.630. Okay, and so that would be the main thing to do to do these calculations is you just need to find the ionic strength. So you just need to work through that formula, work through that summation, and that will let you find activity coefficients. And that concludes our chapter on solid liquid solutions.